Good afternoon and welcome to this class dedicated to thermal properties of materials, which is given in the frame of the lesson Materials and Their Properties at the Federal University of ABC. I'm Professor Mathieu Champeau. So, thermal properties describe the behavior of the material and their application of heat. So the stimulus will be an increase or decrease of temperature, and the response that we are going to observe is either a change of the dimensions of the material. So it can be an increase of the dimensions. So we also say thermal expansion when the temperature is increased, or a contraction when we cool this material. We can observe heat absorption and conduction, and also phase transformation. So let's see some applications that illustrate the importance to know thermal properties of materials, either for the selection, the adequate selection of a material for a determined application, or that illustrate thermal properties that you have already observed. So the first example is the one of containers. So you can see different cups for coffee. So the first one is in ceramic, the second one in metal, and the last one in polymer. And you may have already experienced either the benefit or the disadvantages of each of these materials for this application. So for example, a metallic cup very quickly will hit your hand and eventually burn you because there is a high thermal conductivity for this material, whereas the one made of polystyrene, in fact it is a foam of polystyrene, the thermal coefficient is much lower, and so you can handle it more easily. The second application on the right of this slide is a plastic bottle, but you can see that this plastic container seems to be very brittle. And so in fact, in this case, this plastic bottle has been cooled down below a certain temperature that we already presented, which is the glassy transition temperature. And so below this temperature, the polymer is brittle, and so if you apply a stress on it, a force on it, you can observe that it is breaking. So if the same would have been done at a temperature which is higher than this glassy transition temperature, the behavior of this polymer would have been more, it would have experienced plastic deformation. Then the next example is the one of spacecraft. And so this simulation has been done by NASA that wanted to know what is the temperature experienced by each part of the spacecraft when it enters into the atmosphere. And so you can see that different parts of the aircraft will experience different temperature, and these temperatures are very high. And so in that case, you need to have a material that resists to high temperature, and also that will avoid the conduction of heat that serve as a thermal isolator to avoid the transference of heat into the spacecraft in order to preserve the onboard equipment and human beings that are within this aircraft. And the last example is the expansion joint. So you may have already observed that in huge construction or in civil construction, we use expansion joint because these structures are subjected to high change of temperature. So it may not be so important here in Brazil, but if you imagine the variation of temperature in Canada. So in winter it can be -40 and in summer 35 degrees C. So there is a huge range of temperature to which these structures are submitted. And so during this change of temperature, you have contraction and then expansion of the structure, and this can lead to the distortion or deformation of the structure and failure of this building. And so this is an example of a bridge on which an expansion joint that will compensate this variation of dimension of So let's see some example that illustrate the importance to know thermal properties and that illustrate different kind of thermal properties. So in the first case, it is something that you may have already experienced, is the choice of a coffee cup. So when you want to serve a hot coffee, you can use a ceramic pot or metallic cup or a plastic cup. And depending on the material from which is made your cup, either it will be more easy to handle the cup or not. So for example, in the case of the metallic cup, you know that after a few minutes, the cup will be very hot and it will be it will be very difficult to handle it. Either you will burn your hand, either in the case of a plastic cup, in that case, it is a foam of polystyrene, it is much easier to handle it. And so in that case, we are talking about a property that we will call thermal conductivity. And so metal have a higher thermal conductivity than polymers. And so this illustrates a direct application of this property. On the picture on the right of the slide, you can see a plastic bottle that is brittle. And so this plastic container, in fact, in that case, has been subjected to a force, but also has been subjected to low temperature. So in fact, it has been dipped into a very low temperature liquid and then taken off, and we apply a force. And in that case, this polymer is behaving as a brittle material because in fact it is at a temperature below its glassy thermal transition that we introduced when we talked about polymers. And so depending on the temperature of fuse of this polymer, if it is below the glass transition temperature or above it or above the melting temperature, the properties, in that case, the mechanical properties will be different. Then we have the example of a spacecraft. This is a simulation that has been done by NASA in order to see what would be the temperature that each part of the aircraft would experience when entering into the atmosphere. And so you can see that very high temperature will be reached, and so you need to have a material that has high thermal resistance. And also the second thing to be that is needed for this application, that you need to have a material that will be a thermal insulator. So it will avoid that the inner part of the spacecraft would reach high temperature in order to protect onboard equipment and human beings and so on. And so you need to look for a material that brings these properties. And the last example is one for civil engineering. So in that case, it is an expansion joint that is used in huge structures, for example, bridges or buildings. It is especially necessary in countries where you have high range of temperature. So for example, in Canada, in winter, temperatures can reach -40 degrees C, and in summer 35 degrees C. And so in that case, you need materials that are relatively cheap to be used, for example, on road or on bridge, but also you need to have a structure that resists to this temperature and will resist to the expansion and contraction of this material. And so in that case, in order to avoid problems on the and to compensate this contraction and expansion of the bitumen, we use another material that will serve as a joint and that will compensate this contraction and expansion of the material. And so here we saw a range of applications and products for which the selection of the material is very critical in order to get adequate properties. So in this class, we are going to see how does the material respond to heat. We are going to define and see how to measure the heat capacity, the coefficient of thermal expansion, thermal conductivity, and the thermal stresses resistance. And meanwhile, we will present all these properties. We are also going to present how do metals and ceramics and polymers behave. So the first property is heat capacity. So it is indicative of a material's ability to absorb heat. So the heat capacity is defined as the following. It represents the amount of energy required to produce a unit temperature increase to the material's temperature. So in fact, we are it is measuring the amount of energy to increase by 1 degree the temperature of the material. So it is expressed as the variation of the energy by the temperature variation. And so the unit for the heat capacity, which is represented by this C, it is expressed in joule per mole per Kelvin. Okay, or calorie per mole per Kelvin. And so very often we will use the specific heat, which is written with a small c, which is the heat capacity per unit mass. So it is the amount of energy required to increase 1 degree the material's temperature of 1 mass unit of material. So for example, for 1 gram. So there are 2 ways to measure the heat capacity. Either we can measure it at constant volume for a specimen. So we will use the notation C with a little v, or at constant external pressure. So in that case, it is C with a little p. So constant volume with a v, constant pressure with a p. And so generally, the Cp will be higher than Cv. But this difference is slight in most solid materials at room temperature. So now if we compare the information that are written in this table, so we are comparing water and iron, you can see that the specific heat capacity of iron is much lower than the one of water. So this means, in fact, that it requires lower energy to increase by 1 degree the temperature of iron than the one of water. So let's explain this heat capacity. So in most solids, thermal energy increases by increasing the vibrational energy of the atoms around their equilibrium position. So when we imagine the atoms, when we represent the atoms in a material, we used to represent them at a fixed position, but in fact, they are constantly vibrating at high frequency with a small amplitude. So they are vibrating around an equilibrium position. And this is the case when the material is subjected to temperature either higher than 0 Kelvin. So in any usual cases, the atoms of the material are vibrating. So now we already introduced that these atoms form bonds within each other, and there is spacing distance of equilibrium between them. So the one atom is dependent on the position of its neighbors, and so the vibrations of adjacent atoms are coupled due to this atomic bonding. And so if I want to describe the position of one atom, I should describe also the position of these adjacent atoms. And so when we are talking about vibration of these atoms, we can represent it as an elastic wave. So we can represent that an elastic wave is propagating into the material, and the speed of these waves is around the speed of sound. So here on this figure, you can see what would be the normal lattice positions of the atom in yellow, and the positions after displacement due to vibration in blue. And so you can see it appears like there is a wave propagating in this material. So this is the vibrational vibrational energy of the atoms around their equilibrium position. And so if the thermal energy increases by increasing the vibrational energy of the atoms, we should also say that only certain values of thermal vibrational energy are allowed in a material. So when we say that only specific values of energy can be taken or can be allowed for something, we say that the energy is quantized. And so you may already have heard this terminology of quantization of energy, talking about electromagnetic radiation or light. When we talked about the photon, which represent quantum of energy of light, we said that photon can only take specific values. And here it is the same thing. When we are describing the vibrational energy, we can also describe it using a phonon, which is a single quantum of vibrational energy. So it is a phonon, and its energy is quantized. It can only take some value for a specific material. So now let's have a look to the temperature dependency of the heat capacity. So in this figure, you can see the evolution of the heat capacity with the temperature. And it seems that there are two parts on this figure. There is one on the left part of the figure, from 0 Kelvin to a temperature which is theta D, where there is an increase of the heat capacity with the temperature. And after this theta D temperature on the right part, the heat capacity is almost constant with the temperature. And so we are going to define this specific temperature that separates these two regions, which is the Debye temperature. And so this Debye temperature is the one above which the heat capacity remains constant with an increase of temperature. And so for many solid materials, this Debye temperature is lower than the room temperature. So let's talk first about the left part of this figure. So you can see that below this Debye temperature, there is a huge increase of the heat capacity with the temperature. And in fact, we can, the mathematical model to define it is that the heat capacity is equal, so at a constant volume, is equal to a constant A, which is independent of temperature, times temperature cubic. And the fact that this heat capacity is increasing means that the energy of the waves propagating the vibration in the material is increasing with the temperature. And so since the energy is quantized, we can imagine energy level in the material. And so in this region, some energy levels are available, still available. So we have a dependency of the heat capacity with the temperature. Whereas on the other part of the figure, on the green one, we have a constant value for the heat capacity, which is equal to 3 times R, R being the gas constant. And so the energy of the vibrating waves in the material are independent to the temperature. And so this is due to the fact that for temperature higher than the Debye temperature, all the energy levels in the material are filled. And so this explains the fact that CV is independent to temperature. So we have these two regions in to describe the evolution of the heat capacity of a material with the temperature. So other heat capacity contributions exist, but in fact they contribute to the increase of temperature in a material to a lower extent compared to the vibrational contribution. So we are going to explain it very, very quickly. So there is also the electronic contribution, which means that which exists in the case that we have free electrons in the material. And in that case, the electrons that can move in the material will absorb the energy, the thermal energy, by increasing their kinetic energy. So that way it is only possible for free electrons, because only free electrons can move in the material and can travel in the material. So among the 3 classes of materials that we studied, only metals possess free electrons. And so even in the case of metals, we have only few electrons that are capable of such transitions. So here it is written, it is those close to the Fermi state, and we are going to describe the Fermi state when we are going to talk about electric properties. So that's why I only present it very quickly. But even in metal, there is only a small fraction of free electron that contribute to this heat capacity of the material. So in this table are summarized heat capacity values for a variety of materials. And what we can observe is that the heat capacity value for metals are lower than the one for ceramics, which are lower than the one of polymers. And so, in fact, the structure organization in a material will be favored by the network, will favor the network vibrations. And so in a crystalline ceramic, for example, alumina, the heat capacity is lower than in a case of borosilicate, for example. If we have a look to, by comparing the iron and silver, the difference between the heat capacity of these 2 metals is due to the electronic contribution, which is the second the other mechanism that contribute to heat capacity. In the case of silver, the movement of the free electron are facilitated in comparison to iron. So that's why it is more easy. It requires less energy to increase the temperature of silver than the one of iron. So to summarize, the heat capacity depends on variables internal to the materials, such as the rotation and vibrational energy of the atoms of the material. So that is what we presented. And changes in the energy level of the electrons. So the heat capacity depends in a little extent on structure and microstructure in general, but let's talk about porosity. Porosity is a defect, volume defect, that has a great influence on the heat capacity, because pieces or structures with porosity has lower mass per volume than a bulk material without porosity. So it requires less heat to reach a specific temperature in porous materials. So if you have a look to the laboratory and if you open the oven, you will see that the internal part of the oven is coated with porous material. So it is a porous ceramic. We call it refractory because it can be heated and cooled. It can be heated to high temperature, so it is a refractory ceramic, and it can be heated and cooled much faster and more efficiently than if we would have built this internal part with the same material, but creating dense material. And so in that case, the porosity is useful to make this heating and cooling more efficient. Let's have a quick talk about polymers. So when we talked about polymeric materials, we described the different characteristic transition temperature for these materials, and we introduced a glassy transition temperature, TG. Below this temperature, the polymer is rigid, and the polymeric chains in the amorphous regions are rigid. They are not. They have no mobility. Whereas above this TG, the polymeric chains in the amorphous regions gain mobility, and this is reflected to in the value of the heat capacity. As you can see on this representation, on this figure, the heat capacity at constant pressure increases above the TG of the polymer, and this is due to the fact that it will require more energy to have the propagation of this vibrational wave in the material, because the structure is less ordered above the TG of the material than below. And so it is something that we observe with a specific technique which is called differential scanning calorimetry. It is possible to determine the value of the heat capacity of a polymer below and after and above its TG. So now let's talk about thermal expansion. So what is it and what happens? So now let's introduce thermal expansion. So what is it? What happens? If a solid is cooled, we observe a contraction. So at the atomic scale, we will observe a decrease of the interatomic spacing between the atoms. On the contrary, if we heat this solid, the atoms, the interatomic distance between the atoms will increases. And so the expansion depends on what is happening on the structure. So if we consider a bar of a solid material which has length L0 at initial temperature T0, and we heat it up to this material reach the temperature TF, the final temperature, we will observe an increase of the length of this bar. So the final length will be LF. And so in order to quantify this change in length with the temperature, we use this equation. So we have the variation of the length of the material divided by the initial length of the material, which is equal to alpha L, which is a linear coefficient of thermal expansion times the difference of temperature between the final temperature and the initial temperature. And so in that case, we are focusing on the thermal expansion of the material in this direction, okay, the direction of this bar. So that way we are using a linear coefficient of thermal expansion, but of course, this expansion is occurring in the 3 dimensions, and so we can also have a look to the volume change with temperature. So it is a very similar equation. So in that case, we are observing the change of volume, and so the coefficient that is used in this equation is the volume coefficient of thermal expansion. And many materials are anisotropic, which means that the properties depend on the crystallographic direction along which the dimensions are measured. And so the linear coefficient of thermal expansion will depend on the crystallographic direction on which we are measuring this change, this thermal expansion. In the case of materials that have isotropic, so the thermal expansion will be the following. The volume coefficient of thermal expansion will be equal to 3 times the linear coefficient of thermal expansion. So 3 times this one-dimensional coefficient. So the thermal expansion is reflected by an increase of the average distance between the atoms, and is related to the energy of the bond. So let's see. Let's use this graphic in order to explain the thermal expansion. So at the minimal energy in a material is reached when the atoms are at a distance of equilibrium, and in fact it is the case when the material is at 0 Kelvin. Then if we heat this material, so we will give some energy, thermal energy, to the material, and this will increase the vibrational energy of the atoms. And in fact, when let's say we increase the energy, the thermal energy in the material up to E1, so we will have a change of the interatomic distance, and the atoms will vibrate, and this distance will range from the value given at E1 on the right part of this dual, and between the highest value given on the right part of this dual, corresponding to this energy E1. If we increase again the temperature, let's say up to reaching a vibrational energy E4, so the atoms will vibrate between this position, this interatomic distance, right here, and that one. And so we will consider an average value for the interatomic distance at this temperature. So the average value will be taken in the middle of this yellow arrow. So sorry, that one will be taken right here. So this will be the average interatomic distance at this temperature T4. And so here we show that when we heat the material, we have an increase of the vibrational energy, and so we have an increase of the interatomic distance in this material. And this variation will depend on the shape of this potential energy versus interatomic distance. So if we take the example of this figure on the right of the slide, in that case, we can see that even if we increase the temperature of the material, if we heat it, the vibrational energy will increase, but the interatomic distance won't change since it is due to the shape of this potential duel. So if we continue this interpretation, so we have the dependency of the thermal expansion with the bonding energy, which is directly linked with the value minimal energy right here on this potential energy duel, and also is linked to the symmetry of this curve. So the higher the symmetry and the lower the thermal expansion. So this is the case, as we saw in this slide, the symmetry is high and there is no thermal expansion, even if we have an increase of the vibrational energy of the atoms, but the mean position of these atoms remains the same. So in this first case, we have a high bonding energy because the energy is a minimal energy right here is low, and we have a more symmetric curve, which means that the coefficient of thermal expansion will be relatively small. Whereas in this case, on the right of the slide, we have a low bonding energy because the energy at the minimum of this curve is relatively low, or at least it is lower, and we have an asymmetric curve, and so we can see that the average position of the atom, the average interatomic distance between the atoms, is changing a lot. So it is increasing a lot. So the coefficient of thermal expansion in that case will be higher for this second material. So here we have reported some values for the linear coefficient of thermal expansion for different materials. So for ceramics, it depends on the packing of the atoms. So for example, in the case of silica, the packing is lower, and so the increase of this atomic distance do not entail the macroscopic change in the dimensions. And for alumina and magnesia, it is a little bit lower. In the case of metals, so the coefficient of thermal expansion usually range from 5 to 25, 10⁻⁶ Kelvin -1. Some specific metals have been developed to have a lower coefficient of thermal expansion for some specific applications. And in the case of polymers, so the value for this coefficient of thermal expansion is more higher. This is due to the fact that we have the free volume that increase and the rotational and vibrational energy in this material that increased a lot, and these values are related to the bonding energy in the material. So in ceramics we have ionic bondings that are quite strong, and so that limits that reduces the value of the coefficient of thermal expansion. So in this graphic we also represent the value for linear thermal expansion as a function of the temperature. And as you can see, in the case of polymers, so for example polyethylene and nylon, so the linear thermal expansion will be much higher for a small value of temperature, whereas we have intermediate value for alloys and for some ceramics, and other ceramic like fused silica we have almost no change of this, no thermal expansion of this material up to very high temperature. And so depending on the range of temperature the material will be submitted, we can select a material that have a lower coefficient of thermal expansion, or eventually the contrary, if we have an application for which it is necessary to have an increase of the expansion of this material. And there is a relationship, of course, of the coefficient of thermal expansion with the melting point, since we explained that the melting point increases with the energy of bonding between the atoms in the material, and since we explained that the coefficient of thermal expansion is also dependent on this bonding energy, we can make the following relationship, that the lower the melting point of a material, the higher the coefficient of thermal expansion of this material. And so, as we already presented, this is important in the case, for example, of civil constructions. Here we have the case of rails, train rails, and you can see in these images that the thermal expansion of this material led to a deformation of the rails. So it was not useful anymore, and so now we are using expansion joints that compensate for this thermal expansion and constriction of this material with a change of temperature. And also here is another example of ceramics. So ceramics have strong interatomic bonds, and so low thermal expansion, relatively low. And so we use a material for expansion that we place between all these small pieces of ceramics in order to adequate this panel to the change of temperature. So now let's talk about the thermal conductivity, which is the phenomenon by which heat is transported from high to low temperature regions in a material. So let's represent here a bar of a material. We have one side of this material which is at a high temperature, T2, and the other side which is at a temperature T1. And so thermal conduction will be the transfer of heat from this region of T2 to this lower temperature region T1, so there is heat flow. And so the thermal conductivity, it is the property that characterizes this ability. So in order to present the thermal conductivity, we measure it on steady state flow, which means the heat flow does not change with time. And so we have this equation that represents here Q, which is the heat flow per unit time, per unit area, perpendicular to the flow direction, so it will be the cross-section of this bar. K, it is a thermal conductivity, and the unit it is in watts per meter Kelvin. And this variation of this temperature gradient in Kelvin per meter. And so you can see here the negative sign, which is because it is to represent that the heat flow goes from the hot regions to the cold ones. So the thermal conductivity is this value K. So we can integrate this equation and represent the thermal conductivity through the Fourier's law, and it is quite similar to the first Fick's law that represents atomic diffusion. So here we have the energy transferred as heat per second, which is equal to the thermal conductivity, the area of the cross-section of the material, and the variation of temperature along the thickness or the length of the structure. So let's see the mechanism of heat conduction. So the mechanisms of heat conduction are in two parts. So the first mechanism is the contribution of phonons to the thermal conductivity. So here it is due to the lattice vibration waves that propagate into the material. And so a part of the thermal conductivity is due to the movement of these phonons, of this quantum of energy, from the high to low temperature regions in the material. So the thermal conductivity by phonons is written Kp. Then we have also the contribution of the thermal conductivity by electrons. So the electrons, the free electrons that are in hot regions, have a certain kinetic energy, and so they will move to a colder region, and they will transfer part of their kinetic energy by collision to transform part of this kinetic energy into vibrational energy of the atoms in the colder region. And so this transfer is represented by the thermal conductivity due to electrons, Ke. And so the higher the concentration of free electrons in the material, and the higher will be the thermal conductivity due to electrons. And so the thermal conductivity K of a material is the sum of the conductivity by electrons and by phonons. So what is the mechanism of thermal conductivity in metals? So in metals, we have quite a lot of free electrons, and so the electron mechanism is more efficient. We have Ke, which is highly higher than Kp. And so these free electrons are responsible for both the electrical and thermal conduction. And so we have this Wiedemann-Franz law that relates the thermal conductivity K with the electric conductivity sigma. L is a constant and T is the temperature. So we have this law that relates both electrical and thermal conductivity in metals. And what about metallic alloys? So what is the effect of impurity in metals? Let's remember that when we are talking about alloy, we are introducing other metallic elements to the pure metal, and so we are calling them impurities. So on this figure is represented the impact of the composition of the copper-zinc alloy, so increasing the content of zinc. What is the effect on the thermal conductivity? And you can see that the thermal conductivity is decreasing. And so this means that the alloying element, zinc, is decreasing the conduction by electron. And this is due to the fact that these alloying elements act as scattering centers, and so they deviate the transport, the direction of the electron in the material, and so it lowers the efficiency of electron motion in the material. And if we have a look to this table, so we can see a range of thermal conductivity for all these metals and alloys. We can see that some specific materials have a low value for, even if they are metals, they have rather low value for thermal conductivity. We can also have a look to stainless steel. So stainless steel, in comparison to iron, has a much lower thermal conductivity, and this is due to the fact that a high amount of alloying elements are added to iron in stainless steel. So now in ceramics, there are no free electrons, so the thermal conductivity is due to phonons. Phonons are responsible for thermal conduction. We have the key P, which is higher than key E. The problem is that phonons are not as effective as free electrons to transport heat energy, because in the same way that we presented that the electron can be scattered by alloying elements when we were talking about metals and alloys. Here we have a phenomenon of phonons that are scattered by lattice imperfections. And so the thermal conduction in ceramics is relatively low due to this fact, due to the low efficiency of phonon conduction due to phonon scattering. And if we have a look to this table that show, so we have the third column that represent the thermal conductivity in various ceramics. So we can see that the ones that are glassy, amorphous ceramics, like for example fused silica, have lower conductivity than crystalline ceramics, and this is due to higher phonon scattering, because the highly disordered structure make more difficult the propagation of the lattice vibration in the material. And so that's why we can find in vitreous ceramics and glass value of thermal conductivity that are really low. Okay, but this thermal conductivity evolves with the temperature. Here we have the representation of the evolution of the thermal conductivity of different ceramics with the temperature. And we can see that for most of them, at relatively low temperature, we have first a decrease of the thermal conductivity with the increase of the temperature. And this is due to the lattice vibration that increases and that increase the photon scattering, which make it more difficult, the thermal conductivity. And after a certain temperature, the heat transfer increases due to another phenomenon, which is radiation. So in fact, when it reaches high temperature, we have an electromagnetic wave that is emitted from the hot region, which is an infrared radiation, and that will propagate and be transported in the material to the colder region. And so this this explains why the thermal conductivity increases again after a certain temperature for ceramics. And so for the ceramic materials that are formed by elements with similar atomic mass and similar size, we have high value of thermal conductivity, which is due to the fact that we have low scattering of phonons. So the propagation of these vibrational waves is more easy in that case. For the ceramics that are formed by atoms that are very different in their size and mass, so the value of K is divided by about 10. For amorphous phases or amorphous ceramics, so the conductivity is lower, and so for the ceramics, the vitreous glass ceramics, so the amorphous phase is less conductive than the crystalline phase, even if it has the same composition. And another thing that can be highlighted is that the pores reduce considerably the thermal conductivity. the value of thermal conductivity is low, and the process is slow and inefficient. So due to the thermal conductivity of R. So these are some information that enable to understand the value for the thermal conductivity of different ceramics. And of course, there is an influence of anisotropy on the value of thermal conductivity, on the thermal conduction. So for example, if in the case of quartz, you can see that here the measurements have been done in two directions. So it has been done in the C-axis, so normal to C-axis, and parallel to C-axis, which means two different directions. And by increasing the temperature from 0 to 400 degrees C, the thermal conductivity has been measured, and you can see that the ratio of this thermal conductivity on the two directions is decreasing. So first of all, you can see that the value for thermal conductivity in the direction parallel to C-axis is higher than in the normal direction, and this is due to the fact that this direction is the one with which is the densest, which has a higher atomic density, and the phonons will propagate more rapidly in the directions that are more dense in this material. And you can see that this ratio is decreasing, which is due to the fact that due to the vibration of the lattice, the scattering of this phonon will increase. And so the result is to decrease the anisotropy on thermal conduction in this material with rising the temperature. So now let's talk about polymers. So in polymers, we have vibration and rotation of the chains. So all the thermal conductivity is done by a phonon contribution. When the crystallinity increases, it is the same as what we saw for ceramics. We have an increase of the thermal conductivity because we have more order. And so it is more effective to for the coordination of vibration of the chains in the material. And what can be done if we want to increase the value for thermal conductivity of polymers? Because as you see in this table on the third column, you can see very, very low value of thermal conductivity. What can be done to increase it? We can add mineral or metallic phases, so some particles, and we can create a composite. So for example, a calcium carbonate or carbon black metallic particles enable to increase this value. So finally, let's talk about thermal stresses. So thermal stresses are induced in a specimen as a result of changes in temperature. So first, the stresses result from restrained thermal expansion and contraction. So in that case, these change of volume are restricted due to the presence of another structure or as we can imagine. So in the first case, let's imagine an homogeneous and isotropic solid that can expand in any direction and that is free of movement. So in that case, we will heat or cool uniformly this solid, and we won't observe any temperature gradients. So the temperature will be homogeneous in all the sample. So in that case, we will say that there is no stress. The solid is stress-free. So if we represent the stress by sigma, so sigma is equal to 0. Now let's consider the second case, which is an homogeneous solid, which is isotropic solid with movement that is restricted by a rigid support. So in that case, we have the green bars that represent the isotropic solid, and it is attached to the red solid support. So first, at the beginning, it is at the temperature T0, and then it is heated or cooled to a temperature TF, final temperature. And in that case, we will observe a temperature gradient. So the thermal stress won't be equal to 0, and it is equal to the following equation. So it is equal to the elastic modulus that we introduced in the class dedicated to mechanical properties, the linear coefficient of thermal expansion, and the difference between the two temperatures. And so here we are able to calculate this temperature stress, the thermal stress, sorry. So now let's see the kind of stress that is produced if we place this material between two parts or in a recipient that in a container that limit the that is rigid, and so that limit the expansion or contraction. So let's consider that the rod of this material is fixed to the walls of this container. So let's consider the first example. So in that case, we have rod of material that is heated. So we saw that when we heat the material, we have an increase of the interatomic distance, which results at the macroscopic scale to an linear increase of the size of the rod. And so since we have the walls of this container that limit the expansion of this material, it's like it is applying a compressive stress on our material. It is limiting its expansion, it wants to expand, and the walls are applying a compressive stress. And so in that case, we represent, the stress will take negative value. Thermal stress will take negative value. The second example is the contrary. So we cool the rod of the material rod, and in that case the material tends to contract because there is a reduction of the interatomic distance. But since it is attached to the wall of this container, it is like applying a tensile stress on this rod, like the walls of this container are applying a tensile stress on this material. And so here, the thermal stress is positive. Then we have thermal stresses that result from temperature gradients. So when a specimen is heated or cooled, we have a distribution of temperature on the piece. So this depends on various factors. For example, the piece size, I think it is quite obvious. The bigger the piece and the more the gradient of temperature will be important. The part shape, the thermal conductivity of the material, and the rate of temperature change. And so this occurs, for example, we have high temperature gradients when we apply a very quick heating or cooling of the material that have a low conductivity. So what will happen? We will have the piece of the material, and we will have a quicker change of temperature on the surface of the material. And in the case the material has a low thermal conductivity, it will take time to have the transfer of heat from the hotter parts of the piece, which are on the superficie of the piece, to the intern part, colder part in the piece. And so this means that we have the surface of the material that during heating will expand, whereas the intern part will remain unchanged. of the same temperature, so the same volume. And so we have different parts of the material that will experience different dimensional changes. And so we have a restriction of the free expansion of the surface by the internal volume of the piece. And this creates a thermal stress. So here it is represented. On the left part of this figure, we have a quick heating of the pieces. As I explained, the external part is hot, whereas the internal part at the beginning is still cold. And so we have the expansion of the part on the surface, which is limited by the cold internal volume. So in fact, the external part, which is hot, experience a compressive stress, whereas the opposite occurs on the internal part of the piece, because the external part expands, and so it applies a tensile stress to the internal part. And if the contrary is produced, for example, a rapid cooling, we have the contrary. We have the external part that withstand a tensile stress, whereas the internal part experiences a compressive stress. So its expansion is limited, talking about the internal part. And so this is a huge problem that we face when we talk about materials processing. And for example, when we produce pieces that are injected, made of polymer. So we do, if you remember, we inject a hot polymer, melted polymer, into a mold, and then once the mold is fulfilled with polymer, the temperature of the mold decreases, and so first we will decrease the temperature of the surface of this structure, and whereas the internal part will still be hot. Up to have thermal conductivity and decrease of the temperature of the internal part of the piece, we have thermal stresses that will be created in the structure. And so that's why we observe some distortion and defect in the injected pieces when we don't control very well this process of cooling and of creation of thermal stresses. So what is happening in brittle materials? So first of all, in metals and polymers, since they are ductile, so plastic deformation unable to alleviate thermally induced stress. But we said that ceramics are more brittle and they experience brittle fracture. So particularly by rapid cooling, we induce a stress that is a tensile stress, as we presented. So on the superficie, we have a tensile stress. And when we talked about mechanical properties of ceramics, we said that they are not resistant to tensile stress, to tensile force, and they are much more likely to fracture under tensile stress due to crack formation and propagation. And so if even in this borosilicate cooking plates that is said to resist to thermal shock, you may have already experienced this very bad experience that you took the plate from the oven and then you cooled cold water in it and it totally fractured and destroyed. And so this is due to the fact that ceramic is brittle and does not resist to a tensile stress. And so in order to measure the thermal shock resistance, which is the capacity of a material to withstand such kind of failure, we have this formula, so we can evaluate this T as SR, thermal shock resistance, by considering the fracture strength or the resistance to fracture, the thermal conductivity, the elastic modulus, and the linear coefficient of thermal expansion. So it is it takes into account mechanical properties and thermal properties of these materials. So that's all. We introduced some important thermal properties of materials: the heat capacity, the thermal expansion, thermal conductivity, and thermal stresses. If you have any question, you can send me an email on this address. Thank you very much.